video, we're gonna look at the column buckling experiments results. In our previous lectures, I explained the column buckling theory, and you should be able to locate the previous lecture on this section. If you click the column buckling lecture video, and if you read the description below, this video lecture is a combination of the torsion and column buckling theory. If you want to skip the first part, you can start watching at this time after 1 hour and 11 minutes. Let's click on this video. Right, in this video I covered the column buckling lecture over 1 hour 30 minutes. So if you want to go back and study column buckling lectures, you can click this link and it will take you to the video. And if you want to look at the other additional resources that might be helpful for you to master the column buckling theory, you can look at these videos that I posted. This is the video that shows you, this is a demonstration of the column buckling experiment for pin-ended cylinder column. And there are a few other videos that are helpful for you. Let's look at this one, for example. This is the example problem that has the solution, which was one of your midterm exam problems. So anyway, let's look at the column buckling experiment theory. This spreadsheet will be helpful for you to develop your table for column buckling results. Let's see what we have here. Okay, if you were gonna do the lab report, this was helpful for you to develop your lab report, but in this case the lab report is not required, so all you have to submit just one page summary description, and there are the summary question that we're gonna get into later in this video. But what is important here, this figure is important that tells you the K values for different end conditions, and this equation is important, how to calculate the P critical based on the given modulus of elasticity and the cross-sectional parameters that will help you to calculate moment of inertia. And you can see the moment of inertia calculation for rectangular sections here that I did some calculations on my previous lecture, as well as the effective length, and you should be able to calculate the effective length based on the given conditions by referring to this this figure on the right side. Let's go down. I already worked out some of the examples that I put it in the previous lectures, so you can play with the cross-sectional area. You can change the diameter, for example, from 0.26 to 0.30, which will automatically calculate the elastic buckling load. And let's say for 0.25 I can put 0.15. It will also calculate the elastic buckling load for you, and this table is going to give you automatically the percent error. It also calculates the moment of inertia, which is one of the requirements to get the elastic buckling load. And the yellow highlighted section, these values are measured during the experiment. The measure maximum compression load, which is the maximum load this specimen can take before buckling, and diameter we measure prior to experiment, and the length and the end conditions. So you can use this table to calculate your results given based on the given measured values from the experiment. So how are you gonna get the measured values from the experiment? If you click on this spreadsheet, column buckling data, which also has a definition of your homework or assignment, whatever you name it. Let's click on it. So this is the Cullen-Buckland data from our experiment. As I mentioned before, we already measured before the experiment. We measured the diameter and the length, and we decided the end condition, that how we're gonna connect the end plates. So if you look at the first specimen that has the diameter of 0.23 and the length of 23.5 inches, and the K factor is 0.5, and how I decided to have the 0.5, this column had the fixed end conditions. This is the reason we selected the K value 0.5. If it was pin conditions, pin and conditions, it could have been, the K value could have been 1.0. So the first 1, 2, 3, 4 specimen was fixed conditions, and the remaining specimen were pin connections. Let's continue with the measured maximum compression load. So with this end condition and with the given diameter and length, the measured maximum compression load that the specimen can take, maximum compression load, was measured 315 pounds. And our goal is to compare this value with the calculated result from elastic buckling loads equation. But first, I have to take this equation. I have to get this equation to the spreadsheet right here. This is the main equation, and then I had to look at the equation to calculate the moment of inertia. One second, let me pull up this equation. Well, this equation is already here. I didn't pay attention. So if I want to calculate the moment of inertia for the first specimen, it's going to be pi times d to the fourth, and the diameter is 0.23 to the fourth, divided by, let's put it in parentheses, and it should be divided by 64. Everything is correct. Let's drag it down to calculate the remaining modules of elasticity, remaining moment of inertia values. So we already calculate them. Now I can plug the values of moment of inertia into the cell for EBL value, elastic buckling loads. So for this equation, I have to use 3.14 square times E value times moment of inertia divided by effective length square. So the effective length is going to be the multiplication of the length, the original length, multiplied by the K factor. And I have to take the square. Let's see if it's correct. Okay, so I entered the equation here. Let's double check it. It's pi square times E, 29 million psi, times the moment of inertia, and divided by the effective length square. So once it's done, I can also calculate the percent error. But before that, let's calculate the remaining specimens, EBL values. Yes, there.